Now we'll look quickly at mass spectroscopy, basic definitions and main formulas that we'll need to describe mass spectra. The story started more than 100 years ago when mass spectrum of first samples were collected, showing two different isotopes of neon, carbon monoxide, carbon dioxide, and mercury ions. Today we measure with far better quality. To start with, we never measure mass spectra of molecules. What we measure is always ions, negative or positive. And we never measure mass, we always measure M to Z ratio, mass to charge of ion. Charge of ion is always integer or whole number. Usually it's +1, sometimes -1, but it can be, of course, any integer number. There are two most common ways to represent mass spectra. One is to plot the intensity from your detector as a function of M to Z, so your peaks have some width. And then, of course, you have some noise that corresponds to your background. It's not uncommon just to use cutoff level of, say, 3% and remove all the noise from consideration. Next, for simplification, you can skip the width of the peak and just draw peaks as sharp lines. Then you usually plot M to Z for each of peaks shown. We seldom use absolute intensities. It's very difficult to measure. So most common is to use relative intensity in the group of peaks. Very common name for peak with intensity of 100%, that is the highest peak, the most intense peak in a group, we usually name it base peak. When signal is strong and noise is small, you have a beautiful picture of your signal. When signal to noise ratio is small, you see noisy background and shape of your peak can be corrupted. Very small signal to noise ratios will result in ambiguous peaks. Next concept is resolving power. What is the possibility of your instrument to see two closely positioned peaks, how close they can be? One of the measures, there are several definitions of resolving power. One of them is ratio of mass by width at half height. So one half of height of this peak and width at this position. In this case, you have 0.481 for width, and position of peak is 500, so the resolving power is 1040, roughly 1000. Often we use the reciprocal number for resolution, so delta M by M is 1/1000, or 1000 parts per million, 1000 ppm. So this will be resolution of this particular spectrum. Okay, what about this spectrum? These are lead ions, several different isotopes. Position is 208 for this, and width of the peak at half height is 0.146. So what we do, we take the atomic weight and divide by width. And so that's what we have, 208 divided by 146, 1420, or reciprocal number 600 ppm. Methods that will give you reciprocal numbers of around several hundreds, or resolving power in thousands, we usually say this is low resolution method. They allow to see the difference, say, between 207 and 208 with no problem, but not beyond that point. We also have high resolution procedure, sometimes arrogantly named exact mass. So the masses measured with at least 3 digits, better 4 digits after dot. Keep in mind that mass of electron is very small and can be conveniently forgotten in this case, so we do not care which is the charge of this particle. So in this case, the resolution is around 10 ppm, 100 times better, and we can see differences between masses coming from different atoms. So C5H8O and C6H12 both have formula masses starting with 84.0, but then it's 57 for oxygen-containing compound and 93 for hydrocarbon. So you can see difference of these two. You cannot see them at low-resolution instruments. They will show the peak at exactly the same position. In this particular case, there are 4 peaks with the same number. We name number that will represent M to Z ratio as mass, exact mass, and the whole number we'll name mass number. So 84, 85, 83, this is what you'll have from usual low resolution instrument. 84.057, that we'll have from exact mass instrument. Of course, it's not exact, just higher precision. We know masses of isotopes with more than 3 digits after dot. We actually know 5. We simply do, and very often we know 9 and beyond that point. We do not need usually all these numbers, but 3 are important to see the exact mass. Now, abundances of each isotope sometimes are known exactly. Well, very important are monoisotopics: fluorine, phosphorus, iodine. Almost monoisotopic is argon. Very close to monoisotopic is hydrogen, but it is not exactly. Now, many other elements have several isotopes, like carbon, like oxygen, like nitrogen, like bromine, like chlorine. Some elements have plenty of isotopes with relatively visible abundances. Abundance number is not absolutely certain. There are discrepancies depending on nature and the source of this particular sample.